Okay, guys, let's start our first video lecture for the semester. This will be part 1 of chapter 1. And you'll see on the left-hand side of the screen that I have the lecture slides up. They're shown here. So you should be able to see them. Ah, there we go. I'm trying to mark for you. There you are. Lecture notes over here, and then some slides on the right. Let's look first at these lecture notes. This kind of follows the outline of chapter 1. In particular, binary and hex numbers. I'm going to assume you are ready to go, and if you're not, that you're ready to review expanded notation and conversion between numbering systems. Decimal to binary, decimal to hex. Hex to binary, hex to decimal, binary to hex, binary to decimal. So be sure you can do those, that you're comfortable with that. Now, I know you guys saw this in 2350, however, it may have been long enough time that a little bit of a review is good. So we'll do a very little bit of a review. But if I've put some things out here just to make your review a little bit easier. In particular, there's a table right here that is the base conversions. So this gives you, in fact, let me just show you this one. Okay. And I'm just using the wiki for this, going to the main page, clicking on 2334, and then lecture slides. This will bring up the base conversion table. You'll notice that this table has several different columns on it. So first of all, you've got binary, octal, we're not going to use much, but decimal, hex, for quizzes and exams. If you're not very familiar with this, write this table down, and every time you have to use it, it'll be right there. Over time, the more you use this, the easier this will be. You won't have to write the table. But for now, it's there for you should you need it, which is good. All right, so let me show you the rest of this. Let's go back to the notes. Here we go. Factors of 16. Let me show you this one real quick also, just because this is kind of cool. I've laid this out in flashcards. Now, why is this important? Let me just make a note real quick right here. Do you remember that 2 to the 4th equals 16 to the 1? That means every one hex character can be rewritten as 4 binary digits or bits. That's important because instead of having to write a whole bunch of 1s and 0s, we're going to write hex characters. In order to make these conversions as quick as possible, you need to know multiples of 16. So, multiples of 16 written here in flashcard style so that you can easily go from, oh, I went too fast. So this is the front side. If you print these back and front, or on, what am I trying to say? Front and back page. On the back page, you'll get the answers showing up in red, and the same goes for the rest of these. So print these out. Front and back, two-sided, thank you. And you'll have some really nice flashcards. So 16 times 4, when I flip that over, equals 64 right down here. So awesome. Let me show you, I think I have one more. Practice conversion problems. I won't click through this one. I wanted to put it up here, though, just to highlight the fact that if you need some additional review, I've got plenty of, this is from an old textbook that I used to use many years ago. And it has some great explanation, but it also has a lot of practice problems. So if you're just needing the practice, and guys, practice is what it's going to take to do well, and to be able to do this fast. This is something you were able to do, believe it or not, second, third grade, because you had number sense. You had memorized your multiplication tables. You knew what 7 times 8 was, just with a snap of your fingers. And we've gotten so used to using calculators and computers that we don't have a number sense. So we don't have a sense about, what an answer should be, because we've lost that ability. It's easy to pick back up. It's just memorization initially of rote mathematical facts. So memorize it until it becomes so second nature that you don't have to think about it. Memorization, again, first step in long-term retention in your memory. So, character codes. We have a couple of different character codes or character sets. ASCII it stores a character in 8 bits. It is what we'll see primarily in a lot of what we're doing in your freshman, sophomore year, junior year too. You'll get into some wider character sets, Unicode for one, where a character is stored in more than 8 bits, 16 bits in case of Unicode, which allows you a lot more characters that can be stored. ASCII is sufficient for us because ASCII is really all that we need for what we're going to do. So ASCII is what we're going to use. And let me just make a note here. ASCII is 8 bits. So in binary, 2 to the 8th means I have 256 different characters that can be represented. That's handy. But you'll notice something really interesting. The ASCII character set in hex goes from 00 to 7F. That means that when I write this out in binary, the leftmost bit, or bit 7, is cleared. So I'm only using 2 to the 7th, or 128 characters. So I've got room to grow, but that's also kind of a handy thing because we use that a lot when we're transmitting data to tell if the character I sent was actually the character that was received, because if anything has a bit set in bit 7, then we know something went amiss. That's just one of many, many things we have to check, but it's at least a really obvious way to determine whether a bit was flipped in translation. So when we're dealing with ASCII characters, we know that there's an external representation. In hex, capital A happens to be 4-1 hex. And internally, or in binary, internal I say because that's a machine, this is going to be 0, 1, 0, 0, 0, 0, 0, 1, binary. Lowercase is actually 6-1, or this. A couple of things to notice here. First of all, let me change colors real quick. You'll notice right away that the only difference between upper and lowercase occurs in bit 5. Bit 5, 2 to the 5th equals, 32. So when I look at what is 41, well, that's 4 times 16, or 64, plus 1, or 65. So looking at this in decimal, 6-1 hex is 6 times 16, or 96, plus 1, or 97. Interesting to note that the difference between these two is 32. just as we predicted. Okay, so that's a little bit of what we have there. Let me clear this and show you something else. I want to show you some of the numeric characters, because this is uppercase. Well, let me just talk a little bit about this. Uppercase range. Uppercase range goes from 4-1 to 5A. Whoops. Lowercase goes 6-1 to 7A H. Now, remember we said this goes from 00 hex to 7F. Whoops. Let's go back. F. There we go. That's a little better, not much. So I'm still missing several hex in the midst here. So what happened to the rest of these? Well, I've also got a space, which is a printable character. Well, let's just talk about that. Printable characters. Printable characters go from 20, which is a space, to 7E. Okay, so almost to the very end, not quite. All of those are printable, so those are things including numeric characters, including upper and lower case, including special characters, any of our punctuation marks, things like that. So what comes before that? Well, we've got unprintable characters or control characters that start at 00, which is null, and go to 1F, and then also 7F, or control characters. All right, so that kind of gives you a little idea about character set. Let me mention a couple of alpha characters in particular. Carriage return, which is OD, and line feed, which is OA. When you hit the enter key, these two hex characters are generated and stored. Carriage return and line feed. One thing I've got a prize for whoever asked me this question. Cindy Fry, what does carriage return and line feed mean? Where did we get these words? From whence did they come? If you can answer, or if you can ask me that question, and give me a chance to explain to everybody where they came from, it's really cool. And old, and I'm old too, so well, it all kind of goes together. Get a small prize, first day of class, awesome. Okay, is there anything else that I haven't talked about in characters? I think that does it. So we're good to go. Let's continue talking about what's next on our list. You can't see my mouse. I'm moving my mouse around. We've gone over the general layout. Unsigned and signed numbers. So we'll talk a little bit about this, because what you've done so far in 2350 is really just a review of how to represent numbers, without really regarding sign. You just converted between different base numbering systems. But if you'll go back and look at your notes, you probably never thought, oh, I need to use sign numbers. Well, that's one of the things we've got to do. So let's do that. I'm going to, let's go back. So, representing sign numbers. How do you represent a sign number now? Well, one of the things you do is, let's say, -12. Okay? When I write a negative number in decimal, I am writing it in a format called signed magnitude. What happened to the G? Signed magnitude. I'll just do that. Where I include a sign and the magnitude of the number. If I were to just say this, the absence of any sign would indicate it was positive, because numbers can either be positive or negative. Awesome, so cool, that makes it really handy. So that's how we represent numbers in decimal. Why then wouldn't we think that that would work? Well, a couple of things. Let's move down. Why won't sign magnitude work? Okay, let's go back to our question. And you know what, before I do this, let me go back up and talk a little bit about 8-bit sign magnitude if we were going to try to do this. So let's, in one thing, gosh, that brings up something I'm so glad. Anytime we talk about signed numbers, I have to tell you two things. I have to tell you what format we're using, either signed magnitude or 2's complement, which is the format we're going to be talking about for the rest of this lecture and next lecture as well, video lecture anyway. I have to tell you which format and the length, the fixed length. And here's the deal. We've got, you know, when we do math in our heads or on paper, we don't really worry about length because, you know, I'm limited by the paper that I have. But in a computer, if I store a value, I have to tell the computer ahead of time how much space to allocate for that value. So when I do that, I've also got to indicate fixed length. So let's look at, let's try sign magnitude in binary. And let's say 8-bit signed magnitude. Here I'll show you my 8 bits. And let me change color again so we can go. And I can say, all right, what we're going to do, when we were looking at the decimal, we said, okay, I've got a sign and a magnitude. In my 8 bits, I've got to save room for the same things. So we're going to say that the leftmost bit, or bit 7, in an 8-bit sign magnitude value, or an 8-bit value, the leftmost bit is my, whoa, that didn't turn out well, my sign bit. And then the remaining 7 bits will be for magnitude. So now let's move on, because now when I say, wow, I'm going to really, I really want to use sign magnitude because it's what I'm used to, I can now go back and say, why can't I? And this is really a bad question. In fact, let me mark this out. Whoa, I didn't mean to do that. Well, we'll live with it. Let's mark this out and say, why won't sign magnitude work efficiently? That's probably a better way to put that. Okay, so the reason it won't work efficiently, a couple of reasons. So let me start off with the first one. Okay. Let's say I want to add 2 values. I'm going to add -8 and +5. We know that when we do this in decimal, our answer is going to be -3. Why do we know that? This is important for you to remember. There are rules that we understand in our heads, and we just do them without thinking about them anymore. Here's the deal. When I'm adding 2 values of unlike sign, I subtract the smaller magnitude from the larger, and I get 3, and then I give the answer the sign of the larger magnitude value. And that's how we make this work. Okay? Now, if I just apply in your computer, when I do, you remember simple binary addition facts, 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 1 equals 1, 0. Remember, all these are in binary, and 1 plus 1, 0 equals 1, 1. Okay? With these 4 binary addition facts, I can do anything. Okay? Now, what if and more importantly, I can implement all of these using a circuit called an adder. Whoa, writing is hard. Okay? So with one circuit, I can implement all of these rules. So let's see if with this, and I'm looking for efficiency here. I want addition, multiplication, subtraction, everything to be as quick as it possibly can be. So what I'm going to do is try to apply basic binary addition facts to my problem here. I'm going to rewrite -8 as a signed magnitude, so my leftmost bit will be a 1 to indicate negative. The rest of my 7 bits will indicate the magnitude of the value. Okay, and I'm just going to make a little note that this is signed magnitude. I'm adding to it 5. Well, that's positive, so the signed bit's going to be a 0, 0, 1, 0, 1. Okay, and we add these up, and I get 1, 0, 1, 1, 0, 0, 0, 1. Okay, which in signed magnitude equals negative, that's D for my magnitude, which is 13. So, did I get the right answer? Well, my answer should have been -3. I got -13. First problem with this. Doesn't always result in a correct answer. Correct results. Okay, next problem. Let's go back again to 8-bit signed magnitude numbers. What is this number in signed magnitude? Well, that equals, it's a positive 0. Okay, what is this number? Oh, it's a -0, and you say it doesn't exist, and I say, well, yes, it does in signed magnitude. It surely does. So here's the deal. What this means, a couple of things. If I've got an 8-bit number, 2 to the 8th, I can represent up to 256 values, but now I've got to subtract 2 of those for my zeros, or at least 1 for the extra 0, because I do like 0. 0's handy. I use it all the time. But it doesn't necessarily provide me with efficiency if I'm going to lose another number because I've got both positive and negative. That's a small reason. The bigger reason is we use zeros a lot. And that means every time I check for 0, I have to check for 2 zeros. Do you know how many times you check for 0? When you have a decrementing count-controlled loop, every iteration of that loop, you're checking for the termination condition, which is, oh, is my countdown counter 0 yet? So every iteration of a loop, you're checking for 0. If I have to check for 2 zeros, that means that comparison is going to take twice as long. And again, I'm looking for efficiency. So, second reason, signed magnitude is not going to work. Let's get rid of some of this. Every time I check for 0, I must check for both zeros. So guys, this is not, like we said, this is not the best question, but it's pretty adequate for what we're dealing with. I can make sine magnitude work, but I can't do it efficiently. I can make sine magnitude work by including the rules that we use in our heads all the time, which is when I'm adding two numbers of unlike sign, I subtract the smaller from the larger magnitude, I get a 3, and I apply the sign of the larger magnitude number to my result. If I take all of those rules and implement them in logic circuitry, I can make sine magnitude work. But it means that every addition is going to take 3 times as long. Almost, or yeah, for the most part. So let's stop this one here. We've gone a little bit over, and we'll pick up on part 2.